to do, this is what we're trying to prove, that z is equal to 1 of x at the half gravity. So using this equation, there's a similar problem in the book that has to do with the sphere, and I'll go over this right now. And it's the exact same, you use the exact same steps to solve for this one using the horizontal cylinder. So I'll go over this one now. So in this case, we have a sphere. The shape we're dealing with is a sphere. So what we want to do is we want to start with the equation to find g of the sphere. G sphere is equal to g 4 pi r cubed over 3, that's the mass of the sphere, times z over x squared plus z squared to the 3 half. So the way you guys want to look at it is, we have this here, here's the sphere, the center of the sphere, right here, this is the radius. We're trying to find g, z, gravity, but in the vertical direction, of course. So so our parameters will be, if we go from here to there, this is actually x. So x is going to be negative towards this end. It's going to be positive, and of course it's 0 here. And then so now we're only missing z, which is the depth to the sphere. Can everybody see that? Do you want the lights on? So what we want to do next is, we know that the maximum, we're going to get a maximum gravity when x is equal 0. So we're going to replace x equals 0 here. So at first, maximum gravity x is equal to 0. So the question is, we want to find the half using the half maximum technique. So what we do, we'll deal with two equations, two versions of this equation. When x is equal to 1/2 of the maximum, and then when the gravity is 0. So x will be equal to 0. So the next step is to say, let's find the g of the half maximum of the sphere. Which is equal to, so this one is equation 6 point, just for reference, equation 6.34 in the textbook. So when x is equal to 0, we end up with g max of the sphere. Let me put that here. So the sphere is equal to g4 pi r cubed over 3. And then when x is equal to 0, we get z over 0 squared plus z squared, which results to 1 over z. seeing that. So we end up with, I'll just show it, 1 over 3 z squared raised to the 3 halves is equal to 1 half, 1/6 of z x squared to the 1 half plus z squared. After solving that, we end up with z is equal to 1.305 x 1 half. So you end up doing the same thing for problem 1, just using the actual equation for the horizontal cylinder, which is given in lecture 3 or 2. Any questions? So this is for the sphere. So for the cylinder, you actually want to show z is equal to x to the 1 half, which means there's a 1 here instead of 1.305. Problem 2. So to do problem 2, we have to go over, I'll try and go over the units for the derivation of the actual Bouguer anomalies. So that's going to help you guys know, in order to solve problem 2a, you guys will know what units you name, what phi is supposed to be at, what the elevation is supposed to be at, and stuff like that. So let me do that quickly. Okay, so we'll look at So when we're doing the corrections, you need to notice there is a difference between anomaly and correction. But first, let's start by looking at the two types of corrections you guys will be looking at for the homework, for problem 2. So the two types are, first there is latitude correction, and then we look at elevation, which can be subdivided into 3 air correction, Bouguer correction, and they also talk about terrain correction, which we won't be really looking at for this specific one in class today, for the homework. So there is a difference between correction and anomaly. The anomaly is the result of applying the correction. It's just technical terms, and then they have different little symbols to tell there's a delta in front of one, the other one could be delta G, FA, one could be just